Okay, so picture this, the ICU. It's a place where a patient's life can change in a heartbeat. And the biggest dangers, well, they're often the ones you can't even see. Today, we're diving into an incredible story about how predictive AI and a universal data language are teaming up to spot these hidden threats, giving us a peek into a future of healthcare that's actually happening right now.
Our story kicks off in the ICU with a patient named Rajesh Kumar. Now, if you were to just look at him, you'd think, okay, he seems stable. But his medical team knows the terrifying truth. A sudden, catastrophic dive into circulatory shock can be just around the corner, completely invisible until it's way too late.
And that brings us to the million-dollar question, doesn't it? How can a medical team possibly predict the future? How can they get a warning, not just minutes ahead, but a full 24 hours before a patient's body is about to go into crisis? That's a game-changing amount of time.
So, the hospital actually has this really powerful AI tool that's designed to do exactly this. But it's hit a snag, a really fundamental roadblock. And it all comes down to a data problem. Yeah, this AI is called shock modes, and it's basically a genius at spotting these tiny, almost imperceptible patterns in a patient's body that signal impending shock. The only catch? It can't just read the raw numbers spitting out of the bedside monitor. Nope. It needs the data processed and packaged in a very, very specific format. This slide really drives the point home. Think of it like this. The standard data from the hospital, it's like a page of sheet music with just individual notes. But the shock mode's AI, it needs to hear the entire symphony, the patterns, the rhythm, the complex interplay between all those notes over time. It's a completely different level of information. Okay, so how do you bridge this communication gap? How do you get the hospital's computers to talk to this advanced AI? Well, the solution starts with creating a kind of universal translator for all healthcare data. And that translator has a name: FHIR. For years, different healthcare systems just couldn't talk to each other. It was data chaos. FHIR is the standard that fixes this. It allows everything from an ICU monitor to a pharmacy to an AI server to exchange information seamlessly. It's the essential foundation, the common language. But as we're about to see, just speaking the same language isn't quite enough. Right, because for a super specialized task like predicting shock, a general language is just too broad. We need to create a specialized version of it, a technical dialect, if you will, that both the hospital and the AI can agree on for this one critical job. This is where something called a FHIR profile comes in. If FHIR is the entire English language, then a FHIR profile is like the super precise jargon that air traffic controllers use. It takes the general language and adds a bunch of strict rules and vocabulary to eliminate any chance of misunderstanding when the stakes are this high. It's a custom instruction manual just for our data. So this new shock modes dialect is built on 4 strict rules. First, it demands specific codes for complex features, so the AI knows it's getting, say, time series entropy, not just respiratory rate. Second, it mandates that 24-hour time window, because the prediction absolutely depends on it. Third, it standardizes the number format to ensure accuracy. And finally, and this one is so important, it demands a link back to the original raw data. With this custom dialect all set up, let's see how it actually works. How does this structured data package travel from Rajesh's bedside to the AI and then generate that life-saving warning? The first thing the data message does is it basically announces itself. It has a profile tag that says, "Hello, I'm speaking the shock modes dialect. Here are the rules I'm following." This instantly tells the AI system exactly how to process everything that's coming next. Now here is where things get really clever. The system isn't sending a simple number like 20 breaths per minute. It's sending a pre-calculated, complex feature like respiratory rate time series entropy. That's just a technical way of saying how random or unpredictable is the patient's breathing pattern over 24 hours. A steady, predictable pattern is good. A chaotic, unpredictable one is a subtle distress signal the AI is trained to catch. And this part is absolutely vital. The data package includes a link that points directly back to the raw, second-by-second breathing data from the monitor. This isn't just a technical detail, it's all about trust. It allows a doctor to ask, "Why did the AI say that?" and to follow the data trail all the way back to the source to verify it for themselves. So, with this trusted, standardized system in place, the data flows, the AI analyzes, and the clinical team receives a warning. A full 24 hours before the potential onset of shock.
And the model is good. It has an 83% sensitivity, meaning it correctly identifies 83 out of 100 patients who are truly heading toward shock. And just as importantly, it has a 94% specificity. This means it correctly identifies 94 out of 100 stable patients as being stable, which is crucial for preventing false alarms and alert fatigue in a crazy busy ICU. So what we have here is much bigger than just one case. The story of Rajesh and shock modes gives us a reusable framework, a blueprint for implementing predictive AI safely and effectively in any hospital. The impact here is just profound. A 24-hour head start can be the difference between life and death. We're talking about making a real dent in the staggering 30 to 40% mortality rate for this condition. This isn't just some elegant technical solution, it's a life-saving one. So, what are the key takeaways from this blueprint? Well, it gives us a clear 4-step process. First, it creates a standard so AIs can be shared and exchanged. Second, it achieves true interoperability, where systems don't just share data, they share meaning. Third, it builds clinical trust through that transparent data trail. And fourth, it paves the way for even more complex AI models in the future. When you boil it all down, the entire system works because of this one simple but powerful idea. By taking the time to agree on a data standard, by building that dialect, but create a safe and reliable bridge. On one side, you have the powerful, complex world of AI, and on the other, the fragile, real world of patient care for people like Rajesh. And this leaves us with a really exciting question for the future. We've just seen a blueprint to predict one of medicine's silent killers. By applying this same model of creating specialized data dialects, what else could we learn to see coming? Sepsis? Kidney failure? The possibilities are truly extraordinary.